Hi, and welcome to our next step in the journey, which is statistics for data analysts and data scientists. This forms such an important role in being a proper data scientist, so please, if you're unfamiliar with statistics, take your time and really absorb what's going to be taught over the next few chapters, okay? So firstly, I well know no one likes statistics. Almost everyone seems to have a strong dislike from high school and it stems all the way to college statistics classes as well. It does seem very daunting at times and very much like Greek. And yeah, most people find it quite useless in real life. However, they could not be more wrong. So why is it so important? Well, everyone deals with statistics, we just don't know. Will it rain tomorrow? When you look at the weather forecast, that's basically like 60% chance of rain. That's basically giving a statistic for measuring the probability of rain. Or who's expected to score the most goals in the next World Cup? We all look at like these sports analysts, like their reports and their forecasts for games and events. All those things are dealing with past statistics of how players perform and what they expect, like how much does this guy, like is he good at his home territory? Is he good in cold climates? That kind of stuff. Or is Trump going to win the next election? How do we know? From polls. Polls are based on statistics. It's based on a lot of sampling theory and all these things. And especially, statistics is applicable to business. What month am I going to have the most sales at what time of day? Should I take out insurance on something? Is the economy doing well? So these are all important things that statistics can measure and give us the answers to. So essentially, anything that deals with forecasting and predicting outcomes basically leverages statistics, and companies and researchers who are taking advantage of statistical knowledge, they know what products and movies you like. Think about Amazon or Netflix. Or when fraudulent activities take place, think about those online alerts or calls you get from your bank asking you, did you make this purchase here and there? Or predicting customer demand in future. Or understanding the cause of certain illnesses. All those things can be based on statistical knowledge. Or understanding what the best advertisements are, or the best medications and diets, or even more. So, according to Hal Varian, of the chief economist of Google, being a statistician will be the sexiest job over the next decade, and that definitely has come true since he made this initial quote. So what exactly are the subfields of statistics? Firstly, there's descriptive statistics. These are measures or descriptions used to assess some performance or indicator. Example, batting averages, GPAs, bunch of other stuff. Inference. Now, using knowledge from data to make informed inferences, like answering questions, how often do people get a common cold, or how many people can afford to buy a house at age 25, those are basically inferential statistics. And there's risk and probability. What's the likelihood of you rolling a 6? This is actually extensively used in casinos and insurance companies and finance as well. And there's correlation and relationships. How do we know smoking causes cancer? These were extensive studies done for a long time to actually verify that lung cancer was being caused by smoking. This is, as I said, it's extremely difficult, but it can make very impactful decisions. And there's modeling. That's lastly. Many times in movies or documentaries, you'll hear scientists referring to their model predicts X. Now, in real world, especially in data science, modeling is the bread and butter of the job. Building good models that predict some outcome based on inputs is critical for many industries. Example, predicting which customers will purchasing item A, or what movie would you want to watch next on Netflix. There's so many ways you can build models. It's especially used in advertising as well. Pretty much predicting which ads you would click on. It's also used a lot in economics as well. So modeling is the main focus of the data science aspect of this course. However, we are going to deal with all the other topics in this chapter. Alright, so starting with descriptive statistics, let's take a look and see what it actually is. Descriptive statistics are used to describe or summarize data in ways that are meaningful or useful, such that, for example, patterns might emerge from the data. Now, this is an example of some descriptive statistics. Things like average heights and weights of males in the UK, which is actually the actual stats here. Apparently I'm below average weight, 170, I think. Anyway, the average number of items sold per day in a store. Let's go back to the slide one more time. This is statistics showing basically from this very cool site, Statista. Basically, it shows you the popularity of different social media sites right now, with Facebook still leading the pack, but then WhatsApp second, which is also owned by Facebook. The Chinese one, WeChat, Instagram, also owned by Facebook, and a bunch of others which aren't as popular. Thought Reddit would have been higher, and Twitter would have been higher, but that's okay. That's where they are right now. Okay, so what are some good descriptive statistics? Okay, so let's look at this example here. Let's say we have some point of sale data from a cashier terminal in a store. Okay, we have the item, the description, the cost, the time, and the date it was purchased. Okay, so once we understand our data structure and how it was obtained, we can perform some creative analysis now. We can see that these items here, like this, we basically consolidate on how much each item was sold by description. So we got 2 pencils in this little extraction here that was sold, and this 10-watt bulb and this USB cable. You may remember from pandas, this is basically doing group buys and counts on these item IDs here. This actually should be item ID, not description, by the way. Now, there's one thing you should know is that simple visualizations help us dramatically understand our descriptive statistics, because now we can visually see patterns in the data, and this exploration of data visually a lot is called exploratory data analysis, and it's very important for us to get a better understanding of our data. Now, simply just taking data and computing some descriptive statistics without examining or visualizing the data is the recipe for a bad data analysis. You can have one value in a data set that skews the average so much that basically it messes with everything you've just done. So here's some simpler example of simple exploratory analysis here. So we have a subject here, and these are the marks and scores. Now, looking at this record, we can see the student has 5 subjects. This student has scored a total of 350 marks out of 500. So if we were to look and get the average, his grade would be 70. However, he has a 0 in biology. Is this a mistake? If we ignore the 0, the average is substantially better at 87.5%. So this is an example of having one value here skew the guy's or girl's average all the way down to 70 when it should have been 87.5. And most likely this biology mark probably was 0 because it wasn't entered yet, or perhaps he didn't take the subject, or the exam is in the future. So we don't know. So it's always important to actually check your data to make sure it makes sense. So now we see the need for actually examining our data, and this process is called exploratory analysis, as I just said. So remember, a picture is worth 1,000 words, and this certainly holds true for statistical exploratory analysis. So now we'll move on to the next chapter, which is basically on exploratory data analysis. Alright, so now we start with exploratory data analysis. So what exactly is exploratory data analysis, or EDA? Well, this is a process where we visualize, examine, and organize and summarize our data. So basically, these are some methods of EDA here. We can do all these cool plots. These are called violin plots, or histograms, or bar charts, or box plots, or scatter plots. They're all quite useful, and we're going to go into Python now and actually practice a good bit of these plots. Okay, so let's open the statistics chapter called EDA, the IPython notebook. Let's launch it. And in this notebook, this is basically a visualization tutorial. And we're going to learn a ton of charts we could plot right here. This is a summary of all the plots we're going to do. So the data set we're going to be playing with is called the wine quality data set, which is one of my favorite data sets to look at because it's quite cool. So let's load it here. Okay, there we go. So this is basically the summary of this data set, the first 5 rows. You can see the type of wine, which is red or white only, the acidity, all these different metrics to measure that apparently wine connoisseurs possibly look at. And lastly here, there's a quality indication, an alcohol percentage. So this quality indication is from 0 to 10, I believe, and alcohol basically is just a percentage of how much of the wine is alcohol. So let's do some simple descriptive analysis using pandas df.describe. Okay, so describe looks at all basically the non-categorical or only the numeric columns. So you can see there are a lot more columns here. Well, actually not much more. There were only like, this was the only non-numeric, I believe. Yep. So basically everything else was numeric, and it does some descriptive analysis. It does counts, which is the same for all. It does mean, which is not the same for all. Some are blank apparently. Okay. It does mean, the average for each category. So you can see the average alcohol content for wine is 10.5%, and the average ranking or rating for these wines in this data set was 5.8. You can see the standard deviations, you can see the minimum, the quartiles. We'll get into what these mean later on, but it's just briefly, we're going to just do some quick EDA. You can also see the data type, just to be sure, what I mentioned. Most are float, some are int, quality is an int data type, and type, which is red or white, was an object or string data type. So we can actually get a mean on a particular column just by running this, extracting this column here and running that mean on it. So that's as simple as that. Now let's get into some real cool things, which are the plots. So as we've seen in one of our pandas tutorials before, pandas, you can do graphs quite easily from them and plots. So we can do a histogram by doing df.hist, specify the column we want to do, and we get a histogram here. Now, I don't know if I told you what an histogram is exactly, and I'm going to explain it to you now. So what it does, basically, we have binned the alcohol percentages in categories from 8 to 9, 9 to 10, 10 to 11, and so on. And what these columns represent, this is actually not exactly 8 to 9. This is like a default metric here. We can specify bins afterward. Like, actually, I can show you right now. Bins, let's say bins is equal to 5. Okay. What it does now, it actually breaks it down into these bigger, larger bins here. So before I go on, what I'm going to tell you is that a bin, there's one bin here between 8 and 9.3, looks like. And what this represents here, this y-axis, is how many wines fell into this category. So now you can quickly see that most wines tend to have around 10%. So if you want to get more granular, let's expand bins to 15. You can see the bulk of the wines have somewhat between 9.5 to almost 10% alcohol. This was the most common or most frequent value we saw. So changing bins and doing histograms are quite useful. So you can actually see the distribution shape. So you can see most wines have around 9-10%. Very few wines have more than 13% alcohol, and very few wines have less than 9% or 8.5% alcohol. So that's histograms. Now, as you can see, we can do some more advanced stuff, which I was talking to you about previously. We can change the colors, specify a color here. We can change the figure size by having a figure size argument, 10 by 6. So if you look at it, this is 10 and this is 6. I believe it's inches, I think it's coming up to. It doesn't really translate into inches directly in all screens though, does it? We can take off or turn on the grid. And as like I showed you before, change the number of bins. So let's run this. Also, you can actually enter verbal, or just what we would say, different own colors. So you can put red, you can put blue, English language colors. Blue looks okay. Let's do green. Not bad, okay? So these look nice. However, Seaborn, it's a new library I'm going to teach you now, can produce even nicer looking plots, and it's very easy to use as well, okay? So we import Seaborn as SNS. That's the standard we use. And we can do SNS this plot, okay? And that's what the command for this type of plot is. We can take the column alcohol, similar to how we were doing it here. To specify alcohol, it's a different way of doing it in Seaborn. Set the bins and set the KDE, which I'll explain to you what it is shortly, as false, and then we generate this nice looking plot here. Now, what KDE is an approximation for the distribution here. Just kind of like plots a line, so you can kind of see it. It looks quite nice visually. If you want to just get like some smooth looking surface, but instead of this jagged bar chart or histogram plot. So we can do that, and again we can enter English language representations of our colors. You can change the bins, so it's all quite cool. And I like Seaborn a bit because it produces more static looking plots than Matplotlib, which is what Pandas uses as its built-in plotting tool. So now let's do some styling, okay? Before we go on, I just left this out. We can actually just see the individual counts for the alcohol. Okay, so you can see 9.5, 9.4, 9.2. These are the most frequent, the top 5 counts for it, sorted automatically here. Okay, so let's put this back for you. So now we can do some cool styling. Okay, so Seaborn and Matplotlib both have a lot of cool stylings. Okay, now there's something you should know here. You can actually use Seaborn with Matplotlib. It's a bit confusing to think about, but basically Seaborn leverages some of Matplotlib's tools to plot and label axes. So this is one of them here. So we have the Seaborn plot being generated here. However, we just put it equal to a dummy variable. Okay, and just ignore this for now. So that's a convention of how it's done. And basically then we just create a Matplotlib plot here, and well, not created, just imported the object and created it here, so we get labels to come up. So now we can use Seaborn here as well to control some styling. This is the dark style, which kind of gives, instead of a white background, kind of a tinted bluish grayish background. We can do some cool scatter plots with Seaborn as well. When you hover over it, you get all the different metrics and tools we can use to customize this plot, quite a bit of them. So we're doing a scatter plot of alcohol and fixed acidity, and using the data as our data frame. So by plotting this, we generate this plot here. This line basically just kind of shows you that there's a downward trend here. So basically it's saying that as alcohol increases, the fixed acidity decreases somewhat as well. That's a bit general trend we're seeing here. Same with this one here. This was, we turned the argument here off, fit reg. That's what this was on by default. So let's just plot this. This is alcohol versus density now. So not a cool scatter plot. And again, you can see there's a downward trend here. So let's do some of the cool stuff. By using the LM plot tool in the Seaborn, we can do alcohol and chlorides here. However, we can fit another variable in, which is quality. So by setting, since quality is a nice integer data, we can do it like this. We can actually have quality be a third metric we represent on an XY plot. So it shows you the wine qualities here. So you can see around here, closer to the higher percentage alcohol, and possibly, I guess you can say, lower chlorides, you have some 9s. So these are some top wines here. Similarly, if you wanted to change quality to wine, I believe that should work. No, it doesn't, but that, I mean, it's not wine. I think it was type. Let me just check it to be sure. Yeah, type. Took a while just to check that quickly. Yeah, and we can see definitely. So what does this tell you? This tells you that red wines definitely always have more chlorides than white wines. So again, interesting plot. So let's look at percentiles. I mentioned percentiles when we did the describe command above, but what exactly is a percentile? Now, we know from the alcohol plots, let's just go back to it quickly. You can see there's not much wines that have less than, like, say, 8.5%, and not much that have more than maybe 13%. So having a quartile of 0.1 means that this tells you what threshold is 10%, do 10% of the wines fall under. So 10% of wines will fall under 9.1, 50% will fall under 10.3, 90% will fall under 12.3, and 99% of wines have less 13.4 or less percent alcohol. So that's how percentiles work. That's how the quantile argument, I should say, works in pandas here. So what about the max alcohol content? That's pretty cool. You can just use max, which we've seen before. We can even do quartiles for ranges. So you want to see what alcohol range has at least 5% of the alcohol range in bulk. Let's basically illustrate that here. We're trying to get, we know from this plot here that maybe 5% or 10% of the alcohols are less than here, in this region right here. and the rest of them are here. So when we do a quartile range from say 5%, which might end up being here, like around 9, I guess, to maybe, what was it, something higher, like 12 or 13%, that would be 95%. Yeah, we get this quartile range here. So this is the quartile range is 9, and for 95% is 12. So you can safely say 90%, which is 0.05 to 95, lie within this range. So what about box plots? Now, box plots are very useful, and they basically stem from the quartiles we just described. So quartiles generally are considered the 25% ratios or splits. So one quartile, hence the word quarter, is the first 25%, then the second 25%, which is 50%, then the third would be 0.75, and then the last would be the 100% quartile. So that's what quartiles are, exactly. So using a box plot here, a box plot can give us basically where the median, most common value in the middle is, and the quartile value, the minimum value, the max value, and the third quartile. And we can actually see outliers pretty much here. So let's plot our quartiles using 25% and 75%, which is basically the standard. Now we actually don't need to print this, but we just printed this to show you, this is actually not part of the plot, I should say, but we printed this to show you what the regions are, where the splits are. So by doing a box plot, we can see at 25%, this bulk here, the blue shaded, dark shaded area, is where 50% of the data lies. That's what the box indicates. So the first quartile is here, and the second quartile, and sorry, the third quartile is here as well, okay? So like I said, the boundaries of the box plot here. So technically the first 25% of data lie right here, 25 to 50 lie here, and 50 to 75 lie here. So it is half the data right here, and this is 25%, and the other like last 25% to go to 100%. So you can see this is the maximum, the minimum, and the outliers here as well, okay? Now I should say this isn't exactly a maximum for data, otherwise the maximum would be up here. Now this maximum is basically a formula that's basically Q3, the quartile interquartile range for this here, plus 1.5 the interquartile range. So that's this entire range here is called the interquartile range. So 1.5 times this gives us basically here. All right, and similarly for here as well, okay? Also note these lines here are called the whiskers. That's why it's sometimes called in some textbooks or online resources box whisker plot. So now let's moving on to how we do a box plot with, well, a box plot with more variables. So we can actually plot all the variables here. It's not too legible because the words now overlap, so you probably would want to increase the size of this, and you can change the palette. But now you can actually see this is a pretty cool way. We can actually plot all the data in a box plot and see their ranges, their lies, what the extreme values are, which are these outliers. Outliers are typically considered anything above the maximum or minimum here. Anything that goes beyond those points. So this is a more processed and better looking box plot here. We didn't do it for all the variables, we just did it for about 6 of them. And you can see how it looks. So this is actually pretty cool. We can see these where they lie here, percentage wise, or whatever metrics they're measured in. So this is pretty nifty. Now these are one of my favorite plots we're coming to now, which is violent plots. Now violent plots are very similar to box plots in terms of that box plots we just had the interquartile ranges and maximum minimums for outliers. Basically it's just a distribution, a violent plot. So now we can see, this is a mirror image of it, by the way. They're all like that, just for aesthetic purposes. And you can see basically the bulk. It's basically like an inverted bar chart almost, all right? But it's a nice way to visualize the distribution size too, going up. So you can see slowly going up. For alcohol, is less and less common here. And the bulk of them are again at 9. Now, moving on from violent plots, I'm going to show you a different type of bar plot we can do. So firstly, let's just make the size bigger. And what we're going to do now, I don't know if you looked at this plot, but look at it carefully. What you see here is that we have the quality basically bundled here for each quality metric number. It's 3 to 9. And then we've had it split between red and white on the color axis here. And that's how we did hue. We just put that argument, hue being type, and then we use this axis here for quality, the x-axis, and point the data in the right direction. And there we have it. So a more complicated bar plot that can illustrate some pretty cool things. Now let's look at the Titanic dataset. So Seaborn actually has the Titanic dataset built into it. It's something a lot of people use for experimental purposes. So that's why it comes alongside with the Seaborn package. So now we're going to plot a categorical plot here, it's called, or we can do a nested bar plot. That's also what it's called. And here are the metrics we're going to do. Before we look at it, let's just see. We're going to do the x-axis will be class, the y-axis will be survived, hue, that means they're going to have different colors for each gender or sex. This is our data set that we loaded right here. This is the grid style, basically how the static look of it. The height, the kind, which is a bar plot we're going to do, and the palette, which is going to be muted. And d-spline, basically we just leave it, I'll show you that shortly. And now we just have the y labels below. So let's take a look at this now. So this is pretty cool. This is a Titanic plot now. We can see basically the gender differences now between each. So this is actually really cool. Nice illustration. So you can see there were definitely more female passengers aboard the Titanic than males, first of all. I mean, who survived at least, I should say. So this is pretty cool. You can see males on third class and second class had a very low survival probability, unfortunately. And by the way, this isn't 1%, this is 100%, I should say, just to clarify. Now we can do density plots. Now density plots aren't going to make a lot of sense to you just yet. But what they tell you, I can try to explain to you quickly. Remember I told you how the bulk of the data of the alcohol percentages lied around 9%? Well, this measures density, okay? So the higher you go in a density plot, basically the more dense the region is, and the more contours you'll see. So quickly you can just look at this and be like, oh, there's definitely a concentration of wines here, and maybe a lower concentration over here. All right. Now I realize this plot is actually kind of confusing because it's called density plot, and one of the metrics we're plotting is density. So I just told you something quick that was a bit wrong. It basically, the density is only relates to the contours around it, and this is the density of the wine itself. So yeah, even I have sometimes trouble understanding these plots, but this is a cool one to use. Now what about this plot here, a joint distribution plot? What is a joint distribution plot? Now let's look at it. We have the alcohol, the wine density here, and the alcohol percentages, and what this allows us to do is basically have the distribution on top. So this is quite helpful for visualization as well. Okay, so actually you can see the bulk of these points here. You can see the most common one was like 0.99 something, and this one, the most common, was like 9 point something again. So what about factor plots and B-swarm plots? Now we're getting into maybe a little more complicated plots. To be fair, they're not actually that complicated, but we're going into plots that could just show a lot more data on screen. So for each quality, we're plotting the free sulfur dioxide now versus the alcohol content. Okay, so on the y-axis we have alcohol content, so we can see now if there's a relation between free sulfur dioxide and alcohol and quality. So there's not much we can take away from this, to be fair. They do seem to be almost randomly dispersed. You may have some slight trends in each, but we have to do more statistical analysis to basically extract that. But from right now, from an exploratory point of view, we're just seeing that, okay, this is what it looks like, and you're free to keep changing and trying different variables here. Okay, so this is called the factor plot. Now there's also something called the empirical cumulative distribution function, the ECDF. Now what that tells us here, this is basically cumulative plots. Basically as they go, they just sum up everything. So basically all the wines are basically, instead of having an up-down type plot, it just kind of like builds on it. So you can actually see, so it always reaches the top right as a peak, because this is like percentage. So you can, what this tells us though is that there isn't much we can take away from this one. But remember there was a bulk of alcohol around 9%. So this, you expect the sum to go up higher. That's why you can actually see the jump right here. Whereas the jumps here are much smaller because there isn't much change as we go across. There isn't much wines with these alcohols. So you can see normally ECDFs will start off slow, have basically a jump in the middle, and then smoothen on top. That's how they usually look. And lastly, I just have this line of code here. So basically, if you wanted to read off this data correctly, and you couldn't really tell, 0.2, which is the quartile EDF we're plotting here, corresponds to 9.4, and 0.8, which is up here, corresponds to 11.5, which is exactly as we expected to see. So these are the quantile plots. So you can hopefully use this to understand what the ECDF is telling you. So that's it for our exploratory data analysis chapter and visualizations. This is a very, very important notebook here. So you may want to come back to it every so often and just figure out how to produce these different plots. Thanks. Now let's begin to talk about sampling, or more importantly, how to lie with statistics. So it's a famous quote from Mark Twain: "There are lies, damn lies, and statistics." And I wonder why he said it. So now let's take a look and see why exactly. So imagine a poll was conducted to show 70% of people are supporting Trump in the 2020 US elections. Is that a trustworthy bit of information? How do we even know? So let's see how we can lie with this. First thing to check is how many people were surveyed. Suppose you only surveyed 10 people out of 350 million people. Clearly the accuracy is going to be severely flawed with that poll. Who was surveyed? What if we just asked 10 retired people in Texas and 7 out of them said they would be supporting Trump in 2020? So here's another example of how to lie and mislead with statistics. Suppose there's a scientific paper that said feeding beagles, which is a type of dog, a high rice, low protein diet correlates with high kidney cancer rates. Okay? So now the media headline is going to run with rice, which is a component in 98% of dog food, by the way, causes kidney cancer in dogs. Now, two things here. Firstly, the study never said rice. It says high rice combined with low protein diets. And secondly, this study was done on beagles, not all dogs. Maybe it affects different breeds differently. So you can see, and cancer, when there was a specific type of cancer. So you can see quickly how a media can just misreport a proper study that was done and spread misinformation. So what about something like this? Trump supporters prefer beer to wine. What if the general population prefers beer to wine? Or what if Trump supporters typically lived in warmer states where beer was more popular over wine generally? And what if the actual statistics show that 64% of Trump supporters preferred beer over wine, while 63% of Hillary or Democrat supporters held the same view? Now, this basically is pretty much the same. Depending on how many people were sampled, you can't probably make a definitive conclusion that Trump supporters prefer beer. However, the media or someone can do a faulty study and conclude this and basically spread this. So now this misinformation is going to carry on a stereotypical view where people are going to look at beer drinkers and be like, oh, those are Trump supporters, which is not true because I love beer and I don't support Trump, but that's besides the point. Statistical goal. So now our goal basically is to use as smaller population sample as possible to answer questions about a larger population. And we basically have to find a balance between these. How do we actually find how do we know what size of a small population to use to answer questions about a larger population size? That is our statistical objective here. Exactly. How do you figure out what 350 million people think without asking every one of them? And that brings us to our chapter on sampling. So this brings us to sampling. So let's take a look at the theory behind sampling. So what exactly is it? Now, in reality, if we want to answer a question about a super large population, we can't ask just the entire population. We have to ask a subset of it, a much smaller portion. But how much do we need to ask to generally answer questions about a larger population? So let's do this example. Let's take 5 of your female friends and get their heights. These are the heights of my 5 female friends here. And the average ends up being 5'3". However, the actual average height of an adult woman is 5'4". So my incredibly small sample size compared to 3 billion women ended up being fairly accurate. there was just a 1-inch difference, and that is called sampling error. So look at this chart here. Sampling error increases when the sample size is small, and as the sample size gets bigger or more representative, which is why we have representativity here, the sampling error goes down. So what's good sampling? We want our sample size to be as representative of the main population as possible. This means in our height example, we want women who are tall to be as likely to be chosen as women who are short. We don't want to add any bias there. And this requires our sample to be random. Now let's talk about stratifying data and why it's important. So think about our wine data set. If we use the mean from the entire population of wines, does it accurately reflect the mean alcohol percentage for wines? And the answer is yes and no. Yes, if we're thinking about all types of wines, but generally no, because red and white wines typically have different alcohol percentages. So then mixing them together sort of skews this. So imagine if all reds sort of like hovered around like 10% and all whites hovered around say 9%. By mixing them, you're going to get 9.5%, which is actually not the most common value for alcohol percentages in either wine. So it's a bad representation of the mean. So we need to separate the types and then sample from them. So by separating your data into types, you actually can sample and get that's called stratifying, and get a much more reflective representation of the mean. So tips for creating good stratums. You should minimize variability in each stratum. In our wine example, that would mean removing outliers from each stratum. And good stratas are different from each other. So exactly. So in our case with wines, we know reds are definitely different from whites. However, if we were to stratify based on some arbitrary thing like the density or something like that, it would not be an ideal stratum at all. It would be kind of pointless to do it. So ensure the criteria we use to select stratums are correlated to the property or value we're looking to measure. So in our wine case, that should be different types of wine, which we discussed previously, and they tend to correlate with the alcohol content. Otherwise, it wouldn't make sense. Okay. So why do we need sampling? We're talking about it all this time, but why do we need it? So now imagine you're a data scientist working for a large national supermarket, and you've been asked to determine customer buying habits for meat products. You'll be working with 100 million plus rows of data to perform this, because imagine how much point of sale the data is generated from one cashier, and you have like dozens of cashiers and then hundreds of supermarkets. That is definitely going to be like hundreds of millions of data. Okay, so in reality, you could randomly sample this data set and perform this operation much more quickly with almost the same degree of accuracy. So instead of having to work out means and stuff with this huge data set, we can actually sample from this set. And now what you can do is actually basically maybe even split it up into districts, because you know different areas may have different buying habits and stuff, so you can create stratas like that. So here's a sampling summary. A subset of a population is called a sample. That's what we talked about before. So let's say any subset of like a large population is called a sample. And a good sample aims to be a good representative form of that population. And sampling error is the difference between the parameters or descriptive statistics, that is the mean, of the population. So small sampling errors are good. And the types of sampling that we can use to create good representations include random sampling and stratified sampling. So now we stop at sampling here. We're going to do some sampling examples in Python. So now open this file here, statistics2 sampling. I already have it open right now. So what we're going to do here, we're going to look at our wine quality data set. And what we're going to do, we're going to do some sampling and compare the means of it, all right? So let's take a look at this. Now, this code may be confusing, but I'm just going to illustrate exactly what it's doing. If you have questions about this code, please let me know. I'll just tell you quickly what it does, okay? So we're storing some sampling means into this list. We're extracting the mean, saving the mean initially from our alcohol, or mean alcohol from the population mean. And we're going to do a sample size, a very small sample size at first, which is just 5 samples from our 1600, I believe it's 1600 records in this data set. I can just double check by doing df.shape. 6,000, sorry. I think 1600 was the Titanic data set. So it's 6497 rows. So now what we do here, in this loop here, we take our sample size argument. So we're doing 4 random samples from our alcohol and appending it to this list here. And then we're going to plot those points after the sample means. We're going to plot the horizontal line that shows basically the actual mean. And then we're going to do a scatter plot of the sample means. All right. Sample points, I should say, not sample means. All right. So look at this plot here. So before we look at the plot, actually, let's look at this, what it printed out here. The actual mean from the entire data set is 10.491. Our sample mean is strangely very close to 10.68. So that means our sampling error is relatively small. So, and this is the colors here of it. So red, which is the population mean, which is the true mean. This is our sampling mean. And these were the 5 points we sampled from our big data set. So now let's change this to, let's say 50. Let's see how this looks. So you can see we have points scattered all around here. And now we can see, look at this. Look how small our sampling error has got. It's got to 0.02 when it was 0.18 before. And you can see our actual mean, our sample mean is almost the same thing. So you can, this is a very good illustrative example of showing how when we increase our sampling size, we get closer and closer to the actual mean. So now let's try something here. Let's do 500. So look at this. Look how close the means are. They're pretty much exactly the same. This is like within the margin of error. And it's so close that it actually can't even see the distinction between the lines that it's plotted. So what this tells us is that we can get a very, very close approximation to a larger data set by sampling from it. So by sampling, say 500 from a data set of 6,000, we were able to calculate the means almost exactly as it is. So that's how we were able, as statisticians and stuff, to basically get average heights and weights and stuff of population without actually sampling everyone. So let's see something. Let's try a 100 and see how accurate that is. Again, that's very, very accurate as well. So you can see sampling 100 people out of a population of 6,000 is actually a very good metric to use. So remember this for polling as well. This is a very key statistic you need to know. So let's take a look at stratifying. Remember, stratifying was separating our categories of wines from red and white. So we just do a quick count. We can see we have a lot more white wines in our data set, which is why we should probably stratify them to get them out. So let's create a red and white stratum. This is when it's equal to each. And just double checking the length is correct here. So now let's do the alcohol per wine type. So again, we run this loop here. This is the sample, how many samples we're taking from each one. So let's say 25. Okay. And let's get our, so right now we have our average alcohol percentage for white and our average for red being this. So that's how we actually get our sample sizes, our sample means from different stratums. So let's do 250, see how that looks. And definitely you can see there's it might be very minute, but it can be in some data sets, it could be substantial. So there's like a 0.1514 difference here. So that's noteworthy as well. So that's an example of stratifying, how we can do it, and generally sampling. It's a very good example code here. You can practice with it and get familiar with how sampling sizes affect the descriptive statistics. So now that you've understood sampling, it's about time you can understand the variables in data. So let's take a look at this. So what are variables? So understanding the data you encounter is essential, and it's important you think about data as information you collect to describe something, which means data can now come in two forms: quantitative and qualitative, or also known as categorical variables. So let's take a look at this and what this means. So look at this table here. This table measures, basically it's a report system for examination results for students. So we have first name, last name of the students, we have the age, their general subject area, their overall grade, and their average mark. Now notice these are numeric data, so they're called quantitative variables. They're measuring his age here and his average mark. Now these here, names, sciences, and overall grade, are qualitative or categorical variables. So these are measuring other qualities that are not attributed to numbers, I should say. Although it's important to know, and we'll discuss it later, that categorical variables can have numeric meaning, like grade here. However, generally they're vague and we don't know. So we have to basically extrapolate that meaning afterward. So let's compare quantitative with qualitative. Now, what describes how much in numeric form something is? Definitely quantitative. Qualitative, no. But sometimes it can, but generally no. What about describing a quality or description? No. Quantitative can, but qualitative can. Is it number-based? Yes, quantitative is, and qualitative can be. And it can be in the case of an ID number. An ID number isn't something that you can actually, it doesn't represent a numeric measurement of something. It basically is an ID, like an indicator, like a unique identifier for something or someone. Is a number a quantity? In quantitative it is yes, however in qualitative it's no. And that's why this is important here. Is it string or text? Basically quantitative could be both yes and no. If it's yes in quantitative, it means that there's some string character that we may need to remove to bring it to purely quantitative form. And do words describe a quantity, high, low, medium? Yes, in quantitative, that's how it can be a string data. It can describe something, however in qualitative it can't. So what about nominal or ordinal data? Nominal scale variables differentiate individual data points, example an ID or a name. They say nothing about the value, direction, or size of the quantitative measure. They're always qualitative, okay? Now an ordinal scale, these variables can measure direction, size, or values. However, example for high, low, or medium, or back into this one here, overall grade. As you can see now, overall grade actually can be considered a quantitative type variable because these grades, these symbols here have meaning. And they're basically ordinal scale variables, whereas things like name and stuff isn't, it's nominal. So what about intervals and ratios? Now, interval scales can tell us the size difference between categories. However, they still can't tell us the exact value of, example, date of birth. Okay? So this is an interval example of an interval scale here. You have old, middle-aged, and young. And basically, you know this is what the years they were born. But however, it doesn't tell us the exact date of birth. It gives us like a very vague representation. And this is important because imagine 500 years in the future, we're recording, say, the average age someone had a child, and we have like middle, young, old. It doesn't tell us anything about the date of birth. It tells us the age of the person in a interval type scale measurement. Ration scales or ratio scales are similar to interval, but they have the added property of having an inherent zero. Example, height or weight. So this one didn't. This one we don't even know what the actual boundaries were. However, height or weight is pretty much, we know there's like an inherent zero to that data. Now let's talk about continuous and discrete variables. Now, goals in this table here are discrete. There's no way a player can score a fraction of a goal. So discrete variables measure quantity and value, but they have no interval measurement between adjacent values. Okay? So it's important to remember that. They're just points, numeric points, yes, integer values in most cases, but there are points at that sense that has no in-between value between those points. Height, however, is a continuous variable. Just because we can give a whole number integer values doesn't mean player 1 and player 2 are exactly the same height. This guy can be 177.00 something, like this example here, okay? So they can actually have a slight difference, but it could have been approximated to 177. So in reality, there's no big inherent difference in height. However, because it's a continuous variable, nothing can actually be the same. As I state here, there can be nanometer differences in height. So that brings us to frequency distributions, which we'll now start in the next section. So let's start discussing frequency distributions. So let's go back a step. Why do we collect data? In the science and health world, we collect data to describe some observation we see in the world. In industries or businesses, we collect data to make better business decisions. In engineering, we collect data so we can improve systems, and in social sciences, we collect data so we can describe some observations we see in society. So let's talk a bit about the collection process. We collect data, we analyze data, we use analysis for better decision making, and we've taken a look so far of how we collect data. Now let's explore how we analyze and summarize this data. So let's explore frequency counts. Imagine we have a table of 100 rows of data of student grades and subject area categories, just like this. Now we can use frequency breakdown to summarize this data. Now we've seen this before in pandas where we did value counts, or we did group bys and sum, or in histograms as well, but let's talk about it from a statistical point of view. Now, like I said, if we're summarizing this table here, we're summarizing or grouping by subject area, and we're getting the number of students in each one. So that's pretty cool, and this should sum to 100. So that's essentially what histogram plots do. Histogram plots, basically, in a case like this, we will have 3 categories for histogram below, 3 on the x-axis, and then accounts on the y-axis or the vertical axis. Now, this was our wine data set here, where we have alcohol. As you can see, our histogram plot tells us that there was 1600 plus wines that had an alcohol percentage roughly between 9.5 and maybe just 10.1. So that's what our histogram plots tell us. They're a very good representation of how our data is distributed. That's why it's called a frequency distribution. So let's think about this. How do we know what's a good histogram plot? Okay. Now, here's something here. Our visual interpretation basically is on this axis. Sorry, this is a graph of visual interpretation and the amount of information or detail in it here and number of bins. And you can see our visual interpretation comes down a bit with the number of bins. However, we want it to be able to translate as much information to us as possible. So the intersection between these two is how we basically say it's the best histogram. Now this isn't too scientific, it's just an illustration of a concept here I came up with. And basically it tells us roughly that we need enough bins to help us understand exactly how the data is distributed, and not too many bins that it looks messy or confusing. Like this. This is too many bins here. Because there's too many spikes in between. It doesn't really tell us much at all. It's too granular in this case and spiky. If you wanted to see the very in-between type data types and stuff, alcohol percentages in each small category, you can use this, but generally I'll tell you, this doesn't tell you too much. All it does is just convey that there's a small spike around here. This one, on the other hand, is fairly good. However, it's just too blocky and too vague. It doesn't go as granular as we would want. And let's look at this. This is using, I think, 10 bins, or maybe a little more. But this gives us a very good idea of how our data is distributed. We can see there's a small spike around the middle here. That's between 9 and 11%, majority of alcohols. And it comes down rather slowly here. And it never is below 8% really. So that's what a good histogram looks like. So the rule of thumbs for good plots: remove irrelevant information. The plot with too many bins doesn't show the user that the most common alcohol percentage for wine is just under 10%. And allow your information to tell a story you want it to. Okay? Without showing, or without needing to show further, without requiring the user to be asking unnecessary questions. Okay? So let's go back to this. You can see why this is bad and why this was good. Hope you understand, and that's it for our lesson on frequency distributions. Now we're going to discuss frequency distribution shapes. So we've seen some distributions before. Now let's look at the shapes and see what we can take away from observing the shapes. So imagine we have a data set that looks like this, and you can see here the bulk of the data lies close to the x0 here. However, there's a long drag that's going on to the right side. This is called a right skew or positively skewed distribution. Conversely, if we have the opposite thing, this is a left skew or negatively skewed. And if there's no skew and the bulk of the data is in the middle and there's no drag to either side, that is called a normal, pun intended, distribution. So the location of the tail indicates skewness. So as you can see, the tail here being on the left means it's a left skew. If the tail was on the right, it's right skew. So this is what a normal distribution looks like. Remember I said, pun intended, it can neither be a left skew or right skew. If it's skewed or not skewed at all, if it is a peak in the middle, that's called a normal distribution. And having no peak at all, having a flat distribution like this, is called a uniform distribution. So now let's take a look at a real world example of a normal distribution, and that's one everyone can relate to. It's human heights. So seeing someone who's very, very tall or very, very short is quite rare. However, the bulk of people kind of hover around, maybe for women it's around 5'4", 5'5", and that corresponds to about 160 to 162 centimeters, roughly around there. And for men, likewise, the majority of guys are between 5'8" and maybe 5'11", and that's roughly around 177 centimeters. So this shows exactly how human heights are distributed. And natural things like human heights are always normally distributed. Things like weight as well, or like head shape and eyeball size, all these things are normally distributed. There's natural variation in biology. However, the bulk or majority of measurements tend to correlate or tend to center around a peak, a mean, where everything else is normally distributed. And the extreme large or extreme small values are quite rare. And that's perfectly illustrated in a normal distribution curve. And an example of a uniform distribution is rolling a fair die or dice. After 1,000 rolls, you will expect to have roughly equal numbers of 1s, 2s, 3s, 4s, and 5s and 6s. Exactly what this illustrates here. So let's assume this y-axis is count. You expect to have very, very few variations in all 6 if that die was fair. So now that brings us to analyzing frequency distributions. We're going to take a look at that in the next chapter. Thanks. So now let's get to how we analyze frequency distributions. So we've seen how useful frequency distributions are, but what else can we do? And let's do a fun experiment. When choosing wines randomly in a supermarket, do you have a better chance of choosing a good red or white wine? So now this is a plot we produced from a wine dataset in Python. Now you can probably infer what this plot means, but I'm going to break it down for you. Now the blue is good and the orange is bad. Now we basically set a threshold in our dataset. Basically anything that's below, say 7, I believe we used, would be categorized as bad, and anything above 7 would be categorized as good. And what we can see here is definitely something that's noteworthy. This means that the ratio of white wines to ratio of good white wines to bad white wines is high. It's almost twice as much. Whereas in red wines, it was pretty much even though there's a slight better, more good wines and bad wines. So overall, we can see there are much more good white wines than there are bad wines. Whereas in the red, it's almost equal. Additionally, we can use frequency distributions and analyze them to find outliers using box plots. So these are a bunch of box plots we've created here, separating white and red wines, and for each of the metrics in our data set, and we can see there are a number of outliers we found. They're all circled in red. These are the lower outliers, these are the upper ones. So now let's take a look at how this is actually calculated. And we may have discussed this before, but I didn't formally present it in these slides. This was in Python, we talked about it. So now the general rule of thumb is that an outlier can be described if it exceeds 1.5x the difference between the upper quartile and the lower quartile of the interquartile range. That's above this line and below this line. And let's look at an example. This is what we've done in Python. This is the upper quartile range here. Now this here is the interquartile range. That's 11.1 minus 9.5. How do we get that? Look at it here. 75% of the data lies between here and below, and 25% of the data starts from here and from below to here. So this blue shaded region here is 50% of our data set here. That's the interquartile range. And that takes up a span of 1.6 in the alcohol percentage metric here. So now, how do we get this line and that line? This line is called the upper quartile range, and it's calculated by taking the interquartile range, multiplying it by 1.5, so we get 2.4, and adding it to 11.1, which is this value, the 75% quartile. And that gives us 13.5, which is exactly where this line is. I've indicated it with a red bar right here so you see it. So anything above this range is considered an outlier. So just remember, outliers aren't necessarily bad, but they can skew our data. Basically, they're basically extremities in the data that don't fit the general data set here. That means they don't fit the general, how the data is spread across our population. They're the little exceptions. They're like someone who has a super high IQ in the 180s or something. That's an outlier. They're not part of the normal grouping of the data. And similarly, we have the lower quartile range here, which is 9.5 minus 2.4, which is 7.1. So nothing was below 7.1 actually, so that's okay. So now, let's talk a bit more about outliers. As I said, they aren't inherently bad, though in most data analysts, we often drop them because they were faulty or incorrect data. They are so far off from the bulk or body of the distribution that they can lead to misleading analysis. However, nevertheless, they do sometimes represent extreme statistics that we may need to be aware of. So it could be important to know that maybe sometimes wines that are this extremity here are important for some reason. Maybe they're higher priced or a certain type of wine. So it doesn't make sense to always remove them, but they always should be noted and in our analysis. And note, the definition of our outlier thresholds can be changed according to our own intuition. You don't necessarily always have to go by this rule of thumb here. You can actually define it on your own, and there are different metrics you can use as well. So as I promised, let's look at this chapter here, analyzing frequency distributions. Let's open it up, have it open here. And basically this contains a lot of information we're going to do in the next few lessons. However, I'm only going to browse through the first few cells, maybe the first 10 cells, and that pertains to our last lesson where we analyze frequency distributions. So let's load our wine data set, and remember how we had a plot. Well, this is our quality plot here, so we can just see our distribution of it here. So that's fine. Now remember how we actually had our threshold where we said what was good, what was bad wines. We use over 6 and 6 and under is bad, and above 6 is good. We use a apply and lambda function, conditional here, to create this column called rating, where the wine is either good or bad, as you can see. Okay, so that's how we generated it here. And just a quick reminder, because I know lambda functions can be a bit tricky. All right, let's just make a test function here. So this is how we make a lambda function. This is the input arguments here, and x is equal to x times 2. So this is a lambda function that, FUNC, that multiplies our input arguments by 2. So if we run this here, we get 10. This is exactly the same as this here. However, the lambda is much shorter to write, so it can be used in one-liners like this quite easily. We can also apply a full function as we've seen before, but for now, let's just use lambda. Simpler and more convenient, and this is a Pythonic way to do a lot of these things. So now let's go back to our plot. This is how we generated the plot where we separated white and red wines right here, and their rankings. So we can actually see the white wines are generally rated much better than red wines on average, just because there are twice as many good white wines as there are bad white wines, whereas in red it was roughly equal. Now let's do a count plot. We can actually break it down like this and see how white and red compare to each other here. Now this isn't a terribly informative plot, but it is good to know. So again, just a reiteration of box plots and our columns we're going to do. And this is, what is this again? Sorry. This SNS is missing here. Yeah, this is a box plots here for sulfates, which is not something we really want to see right now, but it's just illustrating it here. However, this isn't terribly important, so you can ignore this for now. And we'll go on to, this is the big box plot slide image I showed in the slides. And how did we generate this? We basically defined our features here, made our plot pretty big, and then we looped through our features by plotting each plot, and we use something called subplot here. This is the grid, so this is tree by tree, and this is the number, so this creates a 9 part grid here, tree by tree. And for each metric here, we use enumerate features to increment I. This is a Python looping tool that I haven't taught you guys before, but it is very useful. I use it quite a bit sometimes. So anyway, what enumerate does, it enumerates features, that's this thing here, this list, and basically by putting I in feature in brackets, we increment I every loop while passing each feature here. So we've created our box plot for feature, our data frame, adding it to our plot, and we create this pretty box plot grid here. So now let's fully understand. Oh, I actually have a tutorial on enumerate. That is so thoughtful and useful of me. So anyway, so this is it here. You can go through this on your own time. It just shows how enumerate works with I. And this is my name, my wife's, and my dog. Also, one of my best friends, his name is Sam. Hope she doesn't think she's that special. Sorry, Sam. And anyway, so this is how enumerate works as well here. Basically, we can go through lists and stuff. So it's a better example again. So now let's look at the interquartile ranges for alcohol in red wines only. That's what we used in our slide. And this was the plot. I don't know if you remember correctly. This was the plot we used here. So by putting orient equal v, we basically turn this from a horizontal box plot. The v is probably better in my opinion, but it depends on how you wanted to visualize it. So that's it for analyzing frequency distributions. There's a lot more we can do through this still. We're just starting, so stay tuned for the future lessons. So we're now about to discuss some more descriptive statistics, and that is mean, weighted mean, mode, and median. So these are also known as summarizing statistics, and we've seen tables and visual representations of our data thus far, and we would have discussed a number of these things just briefly. However, we're going to look at them in more detail. So we're going to see how you can summarize statistics using mean, weighted mean, median, and mode. So you intuitively have a very good idea of what mean is. It is, in fact, the average, yes. So in this example, with these 3 girls here, how many phones they have owned in their life, 6, 5, and 7, you can basically see the mean is quickly 6. 6 plus 5 plus 7 divided by 3, because 3 is the number of people here. Now, there are some common misconceptions. Many times, we consider mean to be the expected average, and that is the center or most common value. However, that is often a mistake. Outliers can skew our means. Joan, with her 26 phones here, skews our mean, because now the mean is 11, and yet none of these girls have 11 phones. So if someone tells you the average height is 5'9", you expect most males to be have that height of 5 feet 9. However, you can see how an outlier, like Joan with her 26 phones, skews that. This is an illustration of mean skewing. See, the bulk of the data is here. However, just having one extreme outlier pulls the mean from where it should be, which is somewhere over here, to here, where there's no one actually has this value, but yet it's the mean. So this is a mathematical representation of mean. Focus right here where I'm hovering over with the mouse. This is mu. This is what we know or call mean in statistics. And mu is basically equal to x1, x2, all the way to xn, divided by n, where n is the number of samples in our data set, and x is each value in our data set. So in our phone example, let's go back to it, you can see that this is x1, x2, x3, x4, and big N, total number of samples, is 4. So let's go back to that. So this is represented what we call with sigma notation, okay? So let me explain what this means here. Let's look at this over here for a second. N is the number of terms we sum to. Xi is what we're summing here, and I is the start or the index of the summation, or the first value. So in our mean example, N is 4, I is basically saying that we started at the first one, and we go all the way up to n, so we take 4 values, and xi basically means that for the first value we sum is x1, x2, x3, x4, and this entire thing is divided by n. Sigma is a very, very handy notation for when we're describing things we do with series data. So you'll see it a lot in this course in future. So let's look at weighted mean now. Here's an issue you might encounter with means. Suppose you're given the summary data below. How can we calculate the mean of the number of cars, the mean of the car's price that's been sold at, okay, over all years? So you may intuitively think that we can just look at this data and just find the mean of these 4 numbers. However, that would be wrong. Okay, think about a simple example here. We have 2 boys and 3 girls. This is the granular data. We have a boy who weighs 101, 115, then a girl who weighs 90, 77, then 99. So the average weight of all 5 of them is 96.4. That's the correct and true mean. However, if you were given the summarized mean separately, so the mean boy's weight is 101 plus 115 divided by 2, which is 108, and the mean girl weight is 88.7. That's the average of 90, 77, and 99 divided by 3. So if you just take this and divide it by 2 to get 98.3, that is wrong. The means aren't equal, and I'll explain to you why. Because you're neglecting to consider the quantities n in this. So you're just looking at this and this, when however you need to multiply this, and you'll see now, multiply it by 2, multiply the girls by 3, get the actual large numbers here, large numbers, and then divide this by 5. So in the case with the car example, let's go back to it. What you need to do is multiply 54 by this, 51 times this, 58 times this, 33 times this, and sum that big large number you get, and then divide it by the sum of these numbers here. That's how you get the true mean, or the weighted mean. Okay, so moving on to median. Many people confuse means and medians. Remember, while means are the average of all the values, median is the average of the 2 middle values, or the actual middle value itself, depending on if the quantity of data is odd or even. So this is an odd example here. Odd meaning it's not even. So we have these 7 numbers here, and the median is going to be the middle number here. Remember, these numbers should be sorted. It can't be in any random order. Once you sort it in ascending or descending, then you can find the median. Now, if it was even, when we had 2 numbers in the middle, so we have 3 here and 3 here, so it's evenly split, the median is this plus this divided by 2. Simple. And these are the means here. Notice they are different. So medians are useful because they ignore the effects of the outliers and give us a good idea of the general average of the data. What does that mean we ignore the outliers? This number could have been 41, or it could have been 41 million. The median stays the same, unlike the mean, which would have been drastically affected. So that means median is a robust statistic. One way to lie with statistics is using means over medians. Example, the average salary of an employee in company A is 100,000 per year. However, that average or mean can easily be skewed upward by a few executives who are making millions per year. In fact, 95% of the company can be making less than the mean salary. So don't believe what you hear. If someone says this company, the average salary is 100,000, that tells you nothing on how much the average employee is actually making. So what about mode? Mode is simply the most frequent term or item in a distribution. In any kernel density plot, remember KDE and Seaborn, the mode is always at the peak. So you can simply see here that mode corresponds to the most common value here. So just before we go into that slide, you can see the mode being here, this value here, or this value here. And it works the same with histogram plots or whatever. You just need to know that the actual data points as being clustered here. So when is mean, mode, and median the same? They are all the same when a distribution is symmetrical. For a symmetrical distribution, we really only need to describe it by stating what the mean is and how wide or narrow the distribution is. And you'll learn what wide or narrow means in distributions later in the next section. So when to use mode, mean, and median? Means are best for numeric, continuous, discrete, or numerically encoded ordinal data, and is good for summarizing the entire population size of a distribution. Medians can be used on the same data type and are good for summarizing data, especially when they are outliers. And you can always use box plots to check to see if they're outliers. And mode can be used on both numeric or categorical data, because remember, it's the most common data in that data set. And they're good for summarizing data for persons who are not well versed in the intricacies of modes and medians. Now, the last slide we'll talk about here is called Pearson mode skewness, and how skewness basically relates to mean, mode, and median. So let's look at this left skewed data. Okay, the left skew means that it's leading to the right. The bulk of data is on the right, but the skew is on the left, so it's called a negative skew as well. Conversely, this is opposite on the right. Now, let's take a look at what the right one first. Mean is just a positive x-axis here. So the mean is greater than the median and greater than the mode. And think about it intuitively. If it's a right skew on the data, that means a lot of data is going to be, like a lot of the larger data set data is going to be here. That means it's going to push the mean from what it should be here to some sort of value on the right. Likewise, the median is always going to be in the middle, and the mode is going to be here. And now for a left skew, it's going to be the opposite now, because this left skew is going to be dragging on here, which is going to drag the mean on this side. Mode is going to be here, and median again is going to be in the middle. So that's it for our lesson on mean, mode, and median, and weighted means. Thank you. So now let's take a look at how we can perform mean, mode, and median operations inside of Python using pandas. So open this file, statistics tree analyzing frequency distributions. And it's a long name here, that's why you don't see the entire name in the previous slide. So scroll down, start from the top so you don't get too confused. Scroll down, which we've done all this previously, straight to mean, mode, and median. So let's load our Titanic dataset here. And let's get the mean age. Now, we've seen mean many times before, but we haven't talked about it explicitly. So to get a mean of any column here, you can just run it like this. Or conversely, if you wanted to get like a summary statistics on everything, you can just do that. That gives you the mean, standard deviation, everything else. Or just run it on the entire data frame, and it works it out for all of the numerical data fields. So you can get the mean age right here. So now let's look at mode, because this doesn't give us mode. It gives us a lot of other things, but not mode. So here's how we calculate mode. Here's a simple function I made that gives us mode. What it does here, it looks at the class, the feature that we're inputting here, which is P class in our example. So it takes a data set and the feature, that's a column name, and we basically get the value counts for it and get the first value because it returns an array of information. We only want the first one, and the first one is the most common one actually, because it automatically sorts it here. So we run this and we get tree being the most common class. So let's try it for age, see how it works. 24. So that's pretty cool. And we can do it for sex, see who's was the most common sex on the board. Male as opposed to female. We did it for age before, so this works. So it's a nice simple function you can use if you ever wanted to get the mode. What about median? So median is quite simple. There's a built-in function for median here, which does this, gives us the median for each of the features here. So we can see the median age was 28, the mode for age was 24, and the mean for age was 29. So that's interesting. So we can get all of them like this here. Quite simple, but we just call it out. And this is another one for the wine data set, which I don't think it's loaded at the moment, but you can do it as well. So have fun with this notebook and have fun with playing with these things. Thanks. Alright, so that brings us to variance, standard deviation, and Bessel's correction. So think about the measure of spread or dispersion in our data. Mean, mode, and median all give us a view of what's the most likely or most common data point in our data set. So think about human heights. We can use mean, mode, or median to illustrate that the average male human height is around 5 feet 9, okay? However, this tells us nothing about how common it is to find someone who's over 7 feet tall or under 4 feet tall. Or even a more descriptive measure, 95% of men lie between what height range? So now that brings us to this range of our data. So in our wine data set, we saw that the max and min alcohol percentages were 14.9% and 8% as a minimum. And this is how we get it here from in our Python pandas code. All right, so range is defined as max minus min. So that's 14.9 minus 8.0, which is 6.9. So that is one way to measure the spread of data. However, there is a flaw with using range to measure spread. The shortcomings of range is that it only looks at the max and min. What if we had a distribution that was like this? 10, 10, 11, 12, 11, 10, 11, 12, and 200. This distribution has a range of 200 minus 10, which is 190, which gives us the impression that our values swing widely up to 190. However, in our reality, our data is consistently varying between 10 and 12 only, and there's only one major exception, which is this point. So now look at this calculation we're going to do. This is our data here, and this is our mean. So the values below mean, so remember mu is our mean, and x is each of our data points. So we can calculate something called distance, which is 10 for each point, minus the mean. So this gives us minus 21 for 10, minus 20 for 11, and so on, okay? So these are the values below the mean, which is everything except 200, which is above the mean. So we minus the mean, mu, from 200, and you get 168. So now the difference, though the sum of these differences here is 168, and the sum on this side is just 1, so it's 168. If you add them up, basically you get, and divide by 9, it's 0, okay? So there's no difference. So that's basically a misleading statistic. So how do we solve this problem? You can use absolute mean distance. So instead of actually taking, go back to this, negative values here, we can just look at positive values, which is the modulus, which is mathematically written as x mod here. Example says if you put minus 2 in this mod, it gives you plus 2. So mean absolute distance is written mathematically as this. All right. So you have the modulus of x1 minus mu, x2 minus mu. This should be a 2 actually, and so on. Okay. So from our previous example, we get this. All positive values, then divided by 9, we get minus 37.3. So that's our mean absolute distance. So what about using mean square distance, which is known as variance? So instead of taking just the mod here, you can actually take the square of it. So instead of doing this in mod, you take a square. So it's essentially the same thing. So from our previous data, we just square each one, and we get this value now. So mean square distance is commonly called variance, and standard deviation is the square root of our variance. So if you take the square root of this now, or of this here in summary, that is called standard deviation. So let's compare variance and standard deviation. Variance measures how far is the sum from the square distances from each point to the mean, and that is the dispersion around the mean. Standard deviation, okay, basically it conveys the same thing. However, there's one weakness in variance that this addresses, and that standard deviation is in the units of our data, whereas variance, because we're squaring it, as you saw in the previous slide, actually this one here, it's 3,530, which kind of means nothing to us. Whereas in this slide, 37.3, that's in the unit, the same unit as our x is here. So it kind of makes sense to us. Moving on. So this is a representation of standard deviation, okay? So now let's talk about something called coefficient of variation, CV. Now, coefficient of variance, CV, is also known as the relative standard deviation, and it is the ratio of the standard deviation to the population mean. Now, what it's used for, it's used to compare accuracy between different standard deviations and means here. So you can look at this experiment here, where the standard deviation was 4.8 and the mean was 120, and this one, different method, it was 4 and 100. And if you just use the CV to compare it, so you put 4.8 over 120 times 100, you get 0.04%. Likewise, you do it here and you get the same thing. So by comparing and the coefficient of variance, the CV, you can show that both methods are equally precise. So now let's talk about something called Bessel's correction, okay? So you remember when we have an entire population and we sample from it, we're sampling and we tend to always get the same mean when we sample. But here's something we tend to haven't mentioned before. Whenever you sample, you tend to underestimate the standard deviation. It's just a natural occurrence, but you can experiment and see for yourself. So when you sample, you tend to just get values that are more commonly around the bulk of the data here. So that's basically here. So let's look at this formula here. By decreasing the denominator, we are increasing the standard deviation. So as the more samples you take, the more likely you are to get the extreme values, and hence the standard deviation goes up. However, when you sample from it, no matter the subset, your standard deviation most likely is always going to be less. So sampling underestimates the standard deviation, and that is known as Bessel's correction. So now let's take a look at how we can calculate standard deviation in Python using pandas. So open this file, statistics tree, have it open here. Scroll down to where we left off from this mean and mode. So it's after mean and mode, standard deviation. And let's reload our wine dataset. And now let's look at this. So we get the mean. We use std.std for after alcohol to get standard deviation. And we just create a plot and we put our mean, we put our lower upper limits here. Let me show you how we calculate this. So we're just defining a lower limit here as the mean minus standard deviation, and then the mean plus standard deviation. We're just drawing vertical lines for it, and we're just putting the different colors and legend and labels, and there we are. So we have the mean, and we have the standard deviation, which I didn't print out, but I will do it now. Okay. So this is our standard deviation here, and let's just print the mean too as well. So the mean should be 10.49, yes. The standard deviation, where the bulk of the data is between. So as you can see, standard deviation measures the spread of the data. It's illustrated nicely in this little plot, and this is simply how you do it here. So it's a quite basic, quite simple thing to do in pandas. Variance is equally simple as well. So now let's print variance here. Actually, it's variance, and print mean as well, and run this plot. And now we can see where the variance lines are as well. Okay, so you can see they're a bit further away from our standard deviation, and that was because they were, if you remember correctly from a formula, they're squared. But because this data is so small, the square value isn't drastically different. However, if this was a larger, longer, bigger numbers, you would see a much bigger spread here. So you can click this link if you want to learn more about standard deviation versus variance. There's a 90-year-old debate on the advantages of each. So I haven't read it in detail. I've skimmed through most of it, and it's probably going to be quite educational for you. Okay. So now let's talk about covariance and correlation. So covariance. So just a reminder, you remember what variance was, right? It measures the spread around the mean, or more accurately, it is the sum of the squared distances of each point from the mean. So covariance is a very important metric in statistical analysis. It is a measure to show the relationship between the variability of two variables. So in other words, we're looking to assess how changes in one variable, our variable here, affect the other variable. So let's think about some data collected for heights and weights of people. We can see as height increases here, so does weight. So what can we say? we can say height and weight are correlated. So how do we measure or mathematically assess this correlation? Okay, this is the formula for it here. Okay, so what we do, we have each x point here minus the mean, and then each y point on the opposite side for weight will be minus the mean divided by n. That basically gives us our covariance formula or metric. So let's look at this. Let's work through a simple example here where we have some x and y points. So you can see the average for the x points are 4.25 and the mean or average for the y points are 0.06. So now let's put these values into this formula. Okay, so I'm not going to read through this entire formula. I'm just going to start it off quickly. So you can see it's xi minus the mean, so 1 minus 4.25, 0.3 minus 0.6, and then so on and so on and so on, divided by n, which is 4. And that is how we get a covariance of positive 0.6. So our result is positive, which means the variables have a positive correlation, which means as x increases, so does y, and vice versa. So the weakness of covariance. Covariance does not give us an effective information about the relationship between two variables as it is not normalized. So what does that mean? This means we can compare variances over data sets with different scales like pounds and inches. It just doesn't work that way. Or it can be very misleading if we did it that way. A weak covariance in one data set may be a strong covariance in another data set using different scales. Let's think about correlation now. Correlation provides a better understanding of relationship between two variables because it is normalized covariance. Normalization is a process of ensuring all variables are of the same scale. Example, imagine we had x in inches, ranging from 100 to 1 to 342, and y in weight, ranging from 50 to 100 pounds. Normalization changes the scale or maps those variables onto a scale that's equal for both. So in this instance, normalization would adjust both scales so they both range from 0 to 1. So what this means now, we're going to map 1 to 0 and 342 to 1. So any value in between here is going to be somewhere between 0 and 1, and likewise for weight. So this is the correlation formula right here. It's quite simple. So basically the covariance by sigma x and sigma y. And basically correlation ranges from -1 to +1. So -1 means a negative correlation, +1 means a positive correlation, and if you get 0, it means there's no correlation. That means they're totally independent of each other. So here's another worked example here on how we can get correlation. So I'm not going to go through all of this technically here. It's the same data we did before. So it's 1 minus 0.425, which is the mean here. Likewise for y, this is the other formula here for the top. So we just take this multiplied by this here. Sorry, actually it is, yeah, that's it. And then we square each of them here. And that is how we get this value here for our correlation. So the correlation matrix, now in Pandas and Seaborn, we can use this to perform some very cool, very helpful correlation plots using this bit of code here. And this is how it is here. So as you can see here, this yellow should probably be more on this one, to be fair, but it has a negative correlation here, and this one is a positive correlation here. So what does this exactly mean though? So you can see this red diagonal here in the middle. That means everything here basically just is plotted against this here. So it's always going to have this positive correlation. So cannot ignore the diagonal values. What you look at now is basically look at the first one here, volatile acidity. Now you can see this is volatile acidity comparing the relationship with the fixed acidity. You can see it kind of has a slight positive correlation with this one. However, let's look at citric acid and volatile acidity. It has a negative correlation. One of the stronger positive correlations we can see here is this one, density and residual sugar. And likewise, you can see alcohol with quality has a positive correlation. And pairwise plots, we can use Seaborn to create some pairwise plots, which are scatter plots for every variable in our data set too. What this means here is like, let's look at sepal width here versus sepal length. This is the scatter plot of both of those variables together. Sepal length versus sepal length, which is the top left one here, basically just ends up being a histogram plot of the distribution. So this is not useful in a sense where we want to look at relationships. Sepal length and petal length, though, you can definitely see there's a positive relationship here, as is this one as well. So this, by the way, is the iris flower dataset. So now we'll take a look at how we can lie with correlations. So now let's take a look at how we do correlation plots in Python using pandas. So open the same file, statistics tree, and scroll down. And we have the code here for correlation matrix. So remember now, we were working with our wine dataset here. That's df. So you can reload it in case it's not loaded. And scroll back down to correlation matrix. So we're going to use Seaborn here. And I'm not entirely sure if Seaborn is loaded, but we'll find out. So what we do here, we run this operation. This is a pandas function here. So we do df.co. This creates a correlation object. And now we create our heat map. So SNS, or Seaborn I should say, takes in the correlation as an input and basically plots it using this nice palette here. And let's plot it and see how it looks. And here we go. So let me show you how to interpret this, okay? So we have a scale that goes from blue to red. And what it's telling us here is that there's a diagonal in the middle, you can see. And that diagonal, let me see if I can just center this a bit. There we go. Okay. This diagonal here basically tells us that fixed acidity has a maximum correlation with fixed acidity, obviously. So you're always going to have this diagonal that is peaking at the top of the legend here in the middle. However, what's important though is what else it correlates with. Okay. So let's look at the next dark red spot. Let's look at this one here. Residual sugar correlates strongly with density. Okay. What else do we see here? Let's look at alcohol. Let's see. Alcohol correlates negatively, well, it has a very little correlation with density. It's not negative. Zero correlation. And then what else does alcohol correlate with? Actually, alcohol correlates quite a lot with density, with quality as well. So how do you interpret this? Let me just explain it to you. What am I doing when I'm looking at alcohol and density here? The quality here is this column here. And this is like alcohol and quality, and we actually see how much the correlation is between each. So this is what these cells or these blocks mean. So you can see for each metric here how much it correlates with quality, and vice versa. Okay, so you can look at sulfur dioxide here, see this dark blue patch, and realize how much it correlates with volatile acidity here. So that's how we interpret this. So another way to consider this is by looking at pairwise plots. Now you can generate a lot of pairwise plots by just running this simple one line of code here, and it generates all of this here. Now this is quite a lot to look at, but let's look at alcohol and quality, since I told you those two correlate. So quality is on this axis here, and alcohol is all the way down here. So you can see, actually you can't tell too much from this because these are categorical variables, so it's not easy to see the correlations themselves. However, in some other data sets here, like this one here, you can see there's a negative correlation going down. It's just a trend. So basically that's what our correlation plots give us. Here's another type of pair plot we're doing here. This is what a KDE, kernel density plot here. So you can actually see better how they look like. So this is this, whatever is on this axis here, versus this one, citric acid. Actually, that's probably citric acid themselves. The plots are in the middle, so everything else just scatters right around here. Okay, and this is another way of doing it here. It's another type of color hue. We use type as hue, so you can actually see red and white wines on these plots here, on these pairwise plots. So just imagine these are just giant scatter plots that help you summarize all the statistics here. So it's very nice to look at. However, you can't often tell much, which is why we do our correlation plot. Let's scroll up from all these pretty plots to this. So you can actually see what correlates with what here. And you can actually see this one, density correlates strongly with residual sugar. So hopefully this was helpful to you guys, okay? And actually, as I scroll up here, I realize I give you all some wrong information. Zero correlation means there's no relationship between them. So that's what this color scheme means here. I actually didn't see the negative sign because it's still a bit small on my screen. But yeah, so basically this color scheme here means negative correlation. So alcohol has a negative correlation with density. And let's see if we can see it from our plots here. So alcohol, and where is density here? Right here. Yeah, exactly. We looked at this one before. So you can see as alcohol goes up, density goes down. So that's a quite explicit correlation we can visually see here. So now that you understand what correlations mean, I'm going to show you how a lot of people get lie with correlations. And we're going to answer the question, are divorce rates in Maine caused by margarine consumption? So clearly from this graph and from this super strong correlation, 99% correlation between them, it appears they are related. However, in reality, what does margarine consumption have to do with divorce rates? Probably nothing. Okay, this is purely probably a coincidence, and possibly could have been just maybe they both correlate to unemployment. So as people got laid off, maybe divorce rates increased or decreased, and vice versa. I'm not even sure if that makes sense. I'm not even sure I'm saying the right thing here. But these two variables they're not caused by one another. So it's important to realize that people who aren't well versed in statistics can often be misled by these bogus claims. And a correlation between two variables does not mean causation. Causation implies one variable is influencing another, and there's no way we can tell from what we've just seen here. So if you want to see some more fun, spurious correlations, go to this website and you'll see a host of other charts that make no sense, okay? But however, the media can always take these results and twist them and create a whole bogus new story about it. And just that's how they spread misinformation. So moving on from this, we're going to take on the normal distribution and central limit theorem. So now let's talk about the normal distribution and the very important central limit theorem. So normal or Gaussian distributions. So far we've discussed mean, mode, and median, standard deviation, and variance. We previously defined normal distributions are when mean, mode, and median are roughly the same. They're often called a natural phenomena, as many things in nature, geography, and biology tend to form normal distributions. So this is exactly what a normal distribution looks like. These are the heights of 14-year-old girls, with the mean being 1.512 meters, and the standard deviation being this. So these are all normal distributions here, and what can you see as a difference? The difference basically is their peaks, which is the steepness of it, and how wide they are. So you can see they kind of go together. If something is steep, it's narrow, and if something is low, it's wide. And look at this one, the yellow one. This one is quite wide. And however, they're all normal distributions, and basically they can be described with only two statistics, that is mean and variance. Okay, what I just said here. So the central limit theorem is one of the most important theorems in statistics, and I'll get to why. However, the central limit theorem states that the sampling distribution will look like a normal distribution regardless of the population we're analyzing. So this doesn't tell you much yet. However, we're about to see it in action. So take a look at this. This here, in this green circle, is basically the full population here. And these little circles, the red circles and the yellow circles, are all sample distributions. So we're just taking random samples from this. So what does that say? Okay, these are all sampling distributions here. So take a look at this here. This is our population distribution here. And each one here is a sample. Okay, so let's go through the steps. So imagine we're sampling the distribution shown on the left, not right. Okay, we take several samples, 2 to 6. Okay, so these are some samples we pulled out here, a sample we pulled out here, a sample we pulled out here, here, and here, okay? And these are the red dots are actually the means of it. So this is basically the points we sampled, where they lie. So they can lie in the extremities, the mean is still here. These can lie a bit more uniform, mean is here. These can lie basically sort of like a bit more on the left-hand side. Mean is here, mean is over here, and here. And yet, guess what? When we put all these means together, we end up with something that looks like this. It follows a normal distribution. And that is the power and beauty of the central limit theorem, in that whenever we're sampling from a distribution, we always end up getting a normal distribution. That's exactly what we said here. Okay? Regardless of the population we're sampling. And you can try this experiment here on this website. You can click this link in your PDF that you have in your resources, and you can actually experiment with it as well. You can change this parent population here, sample from it, different sizes, and you'll see you'll always end up with a normal distribution. So now let's take a look at z-scores. So now let's take a look at z-scores and percentiles. So let's do a refresher on standard deviations. So imagine this is the plot from a wine data set of alcohol. Remember, they peaked at around 9 point something, 9.4 I believe. And this plot here shows the mean here, which is mean alcohol content, which is 10.4 I believe. And this is its first standard deviation here in the red units. And the lines I've labeled here, this is 1 standard deviation away, this is 2 standard deviations away, and this is 3 standard deviations away. So imagine we pull a bottle of wine at a grocery, and we see its alcohol content is 13%. So from our standard deviation plot, we see that 13% exceeds the mean alcohol content by quite a bit, right? All the way over here. So how different to the mean is 13% really? It's approximately 2 standard deviations away from the mean. As you can see, it's here. It's just about a little bit over. So what is z-score now? So logically, what we did is that we took our 13% sample value x, subtracted the mean, and then divided that mean by the standard deviation. That's exactly what we did. So we have x, which is our 13, minus the mean, which was 10.49, divided by 1.19, which is our standard deviation here, and we got 2.1. This is how we know it was just over 2 standard deviations away. And that's what the z-score is. It's basically a distance relative to standard deviations. And z-scores indicate that the value is larger than the mean. A positive z-score means that's larger than the mean, and a negative z-score implies that it's negative from the mean. Because if it was a smaller number here, that means it would have been negative, because this would have been smaller minus a larger number. So now we can transform an entire distribution by doing a z transform. And what a z transform does, it basically sort of like normalizes the entire distribution here in this scale here. So we now have a density scale, and this here. So the entire area of this curve is now 1, and we sort of have the mean at 0. So notice the entire shape is preserved. However, it's now transformed into the scale. So this is the code for how we actually calculate the z-scores in Python, which we'll do shortly. So why do we use z-scores? Z-scores in general allow us to compare things that are not normally in the same scale, as long as they're normally distributed. Example, think of the examination results for 2 different subjects. Now this is a very good example, and probably all students can relate to this. So Ryan's mark in class was 24 out of 40, and class average or mean score was 22, and there was a standard deviation of 10. Sarah's mark was 39 out of 50, and the class mean was 34. So in both cases, they did do better than the average, and her standard deviation in her class was 15. So who performed better relative to their peers? Now we can calculate that by looking at z-scores. Okay, because remember, z-scores measure how far this x is here from the class average relative to the standard deviation. So we go 24 minus 22 divided by 10, which is 0.2. And Sarah's z-score is 0.3. So therefore, Sarah performed marginally better in her examination score. So now let's take a look at this. This brings us to how we can use z-scores to determine your percentiles. Let's go back to our previous example where Ryan's score was 0.2 and Sarah's was 0.3. So Ryan, looking at this z-table here, and you could find z-tables all over the internet. This is just a random one I pulled from this site web here. So you can go to Google Images and search for z-table. So how do we use this though? Okay, we see that Ryan's score was 0.2. So you look at the z-score of 0.2 and you can quickly see here it was 0.57. He's in the 57th percentile in his class. Oh, sorry. Conversely, Sarah was 0.3 and you can see Sarah would have been 0.61. She's in the 62th percentile for class. So what is this table? What is this column here? Basically, as you can see, it's 0.2. What if Ryan was 0.25? That's where this table, this line comes in. So 0.25 would be right here, 0.59. And understandably, that means he's in a higher percentile, because the higher your z-score you go, the higher your percentile that you're in. So that's it for z-scores and percentiles. So let's quickly take a look at z-scores in Python. So it's in the same notebook, statistics tree, and it's all the way down after all these pairwise plots at the bottom of this notebook. So let's quickly see this. Now, let's hope this data is still there. Yeah, it is. So remember this plot where we plotted the standard deviation lines? This is how we've done it here. So we have the STD that we got right here, and we have DDOF, which is degrees of freedom, which means that we divide by n and not minus 1 when we have it equals 0. I'll explain to you later on why we do this. However, it's not too important. It doesn't affect things that much at all. We get limits here, max and min, and we just create a plot right here. Max and min would be these limits, I should say. And these are different lines, and 13 was our sample alcohol, so we just plot a line for it here. So that's how we generated this plot. And we can do a description of the statistics to just make sure STD is here. And now let's look at this. This is how we convert our distribution, or regular distribution, into a z distribution. So now here's what we do. We basically convert it using this formula here. So we get the z-scores from alcohol. Remember, z-scores were the x value minus the mean divided by the standard deviation. That's what this lambda function does here. And we just apply it to this column by using the apply function. So it's quite easy and simple to do. And we just generate the plots right here. So we create a subplot grid, 1 row, 2 columns, plot 1, plot 2, and we just plot it with our limits here and get our max and min, and that's it. Oh, if we don't use this, like I said, the plots will overlay. Well, actually they don't, but they actually can have some overlay with the words. So that's why we do this sometimes. And basically now, this is the z-score stuff here. So z mean area is equal to this. Z mean and the z standard deviation is equal to this, with our degrees of freedom being 0. And we can just print these things here, and you can see this is correct. So now, what does this mean? This is effectively 0, by the way. Our z mean is supposed to be 0, and it is effectively 0 because this is 4.9 times 10 to the minus 14 power, which is like 14 zeros before. And this is the mean here, standard deviation I should say. It's 1. So we've normalized our distribution here using our z-scores, z-score techniques. So that's it for z-scores. We're now about to move on to a new topic called probability.
Subscribe now and press the bell icon. Never miss an update.